Yeah, good morning, dear students. Uh, Yesterday, the previous class, you understood how to write an assembly code and optimize the performance of the assembly code. And the first technique that you understood in order to optimize the performance of the assembly code is instruction scheduling. Uh, uh, that is what you understood in instruction scheduling. You understood uh, uh, how to efficiently reorder the instructions within the program in order to maximize the performance of the program. And then you also understood the loop unrolling technique, and we understood three different programs there. The first program to convert a single character from, yeah, if I just go back and show you, uh, yeah, this program to convert a single character from uppercase to lowercase. So it was taking total 11 clock cycle, so I have explained it in detail. 11 clock cycle, and later, after applying the technique of preloading and computing the cycles, it took 9 cycles, and the performance of this program was 1.22 times more faster than the original code. And similarly, we further enhanced the further optimized the program by using the technique called as loop unrolling. So that means here the loop was unrolled for three times. That means this BNE instruction which we used to write here, it was an override instruction, and it used to consume 3 clock cycle. Now by unrolling the loop for 3 times, we avoided the BNE instructions for 3 times. Correct? 3 times. This is the code which was written after unrolling the loop for 3 times. And when I computed the clock cycles for this code which is unrolled for 3 times, I got 21 cycles. That means 21 cycles. So 3 characters you're able to convert from uppercase to the lowercase. That means you're performing 3 iterations in the 21 clock cycles. And to perform one single iterations, you require 7 clock cycles, or to convert one single character from the uppercase to lowercase, 7 clock cycles are required. So in the first example, you it was 11 clock cycles required to convert one character from uppercase to lowercase. In the second example, it was 9 cycles, and in the third example, we have reduced it from 11 to 7 clock cycles. And when I compute the performance of this program, the program which is unrolled for 3 times, with the performance of the first example, it takes 11 by 7. 11 is the time taken, or the clock cycle taken, by the first example in order to convert one single character from uppercase to lowercase, and 7 is the total number of clock cycle taken by this program, which is unrolled for 3 times in order to convert a single character from uppercase to lowercase. Now the answer is 1.57. That means the performance of this program is 1.57 times more than the performance of the first program or the original program. So now the next topic is register allocation. Now here we are going to understand how to allocate the register for various variables, and how to hold the data that is being used for performing the computation in the registers. And as you all know, there are 16 visible ARM registers. 16 visible ARM registers, and in this 16 visible ARM registers, 14 registers are used to hold the general purpose data, and the remaining 2 registers in this are stack pointer and the program counter, and these two cannot be used for holding the general purpose data. So 16 are visible ARM registers. Among these 16, 14 registers can be used for holding the general purpose data, R13 and R15. Since R13 is reserved as a stack pointer and R15 is reserved as a program counter, these two cannot be used for holding the general purpose data. R14 acts as a link register, you already know that. So at some point of time, even R14 can also be used for holding the general purpose data. Now, these are the visible registers, and 14 registers can be used for holding the general purpose data. 13 and 15 cannot be used for holding the general purpose data. And there is something called as ATPCS, that is ARM Thumb Procedure Call Standards. Now, when you are calling the function from the ARM code to the thumb code, or thumb code to the ARM code, so they got to follow this standard. So that is named as ARM Thumb Procedure Call Standard compliant. It must preserve the Kali values of the values of register R14 to R11. Now, whenever there is a procedure that is called from the either from the ARM code to the thumb code, or thumb code to the ARM code, all these registers, so R4 to R11, must be preserved. That means they must be saved before calling the procedure either from the thumb code to the ARM code, or ARM code to the thumb code. So this is what you have to remember. This is what the standard says. ATPCS standard says that all these registers R4 to R11, they must be preserved whenever you are calling the function from ARM code to thumb code, or thumb code to ARM code. And one more important thing is the ATPS standards also suggest that the stack should be 8-byte aligned. Now, when you are storing something onto the stack, it must be saved at an address which is multiple of 8 bytes. When I say 8-byte aligned, so when you are storing something onto the stack, the stack address must be a multiple of 8 bytes. That means I say I have a word to store to the stack. I can store it at address 0, because 0 is a multiple of 8, because 8 into 0 is 0. And then after 0, what is the address that I can store the next element? It is at address 8, because 8 is a multiple of 8 again. 8 into 1 is 8. And after 8, now which is the next address I can store the word? It is 16. After 16, it is 24. It goes like this. That means when I say 8-byte aligned, so the address where you can store the data must be a multiple of 8 bytes. And similarly, if I say 2 bytes aligned, the address must be a multiple of 2. Similarly, if I say 4 bytes aligned, the address must be a multiple of 4 bytes. Now, with this slide, you understood 16 visible ARM registers are there. Among the 16 visible ARM register, 14 registers are used to hold the general purpose data, including the LR register, which is R14, but R13 and R15, they cannot be used to hold the general purpose data. And there is a standard called as ATPCS that must be followed whenever you are calling the procedure from the ARM code to the thumb code, or thumb code to the ARM code, and all these registers must be preserved before calling the function. That is what this ATPS standard says. And one more important thing, what it also specifies is that when you are storing something onto the stack, it should be an 8-byte aligned. Now, what is the meaning of 8-byte aligned? So the memory should be the data what you store to the memory, it should be a multiple of 8 bytes. The address must be a multiple of 8 bytes. Next, so template for optimized assembly routines requiring many registers. Say I need to use too many registers. Now we told you can use 14 registers for holding the general purpose data. Now if I need to use all the 14 register, and if these registers are already holding some specific data, then what I have to do? So there is a simple technique. What you can do is this. See, now there is a need for me to use all the registers from R4 to R12. Now here I am saving, including the link register from R4 to R12 to the stack. Now STMFD is store multiple full descending stack. Now I'm storing the content of register R4 to R12, including the LR register. And then here goes the body of the subroutine, and the moment all these registers saved onto the stack, you can go for using all these registers inside the body of this routine. Now after that, now once you're done, you can again get the data which is stored onto the stack, and put them back into these registers. So R4, R12, like this. Restore registers, and you return back the control. So this is what the simple template which we use. If there is a need for you to use the too many registers, and if the registers are not available, so the one simple technique that time for you people is to use the stack, store all the content of the registers there, then use those registers accordingly, as you need, and finally you finished with performing the computation. Just restore back the registers from the stack using the pop operation. LMD is from the stack you're loading all these registers. Now there is one more important thing to remember here. See, I told in the previous slide, so whenever you're calling a procedure, you got to restore you got to preserve the registers R4 to R11. Now we have written here from R4 to R12. The only reason the R12 is also stacked, just to keep this stack 8-byte aligned. Now R4 to R12, if I count, so R4, R5, R6, R7, R8, R9, R10, R11, 11. So totally it is 8 registers from R4 to R11. If I assume the R4 register content is starting from address, it can start from the address 0, and then 0 to 3 it will go. Next R5 content will go from 4 to 8, and like that. If I go 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7. 0 to 7 is nothing but 8 registers. Here I have R4 to R11, I have 8 registers. 0 to 7, 7 into 4, 28. But 28 is not multiple of what? 8. Now that is the reason I am including R12 also. If I take R12 also, if I save onto the stack the R12 register also, now it is 9 register in total. When I count from 0 to 8 it will become. Now 0 to 8, 8 into 4 is 32, and 32 is a multiple of 8. So only for that reason we are also stacking the R12, just to make the stack as 8-byte aligned. Address starts from 0 and ends at 28. For R4 to R11 I am returning 28 is not a multiple of 8. Now and if I stack R12 also, address starts from 0, ends at 32. For R4 to R12. Say R4 will start from 0, end at 3, and then R5 starts as 4, ends at 7, it goes like this. And finally R12 will end at 32. Now 32 is a multiple of 8. Now R1 need not be stacked if the routine does not involve the ATPCS routine calls. That means if you're calling the routine from ARM code to the ARM code, or if you're calling the routine from thumb code to the thumb code, then you need not stack this R12. Now this stacking R12 is required only if there is enter call, that is your ARM code is calling the procedure which is there in the thumb code, or the thumb code is calling the procedure which is there in the ARM code. I hope you people understood this. That means whenever there is a need for you to use too many registers, so the one simple technique which you can use is stacking the registers from R4 to R12 including the LR, and then you can use all those registers here. The moment you're done with the computation, you can just restore these registers back from the stack. Now next, for ARM5 and above, you can use the preceding template even when being called from the thumb code. So the same template can be used for all the processes which are ARM5 and above. For ARM4 and below, you have to use the following template, because ARM4 and below, they don't support this. Now what we this is what we have written here. Now what we have to do is, for returning BXLR we have to write. So here what we were doing, so we were popping this and we are putting it into the PC, so that the control used to get returned. But now you pop all of them and then you got to explicitly write BXLR. This we have already understood in the previous session. Now ARM4 and below, So this is what the template which we'll be using if there is a necessary for you to use the too many registers, and for ARM5 and above, if there is a necessary for you to use too many registers, and this is what the template will be using. Now allocating registers to allocating variables to register numbers. So it's best to use the alternate names to the registers rather than the explicit register number. This is what we understood even in the previous class. I showed you can give an alternative names to the register numbers. So by using the assembler directive rn. Now it is always a good practice to give an alternative names to the registers instead of using the direct register numbers. Now what are the benefits of using the alternate names? So the one benefit of using the alternate name is it allows you to relocate the register numbers easily. If you have used the alternate names, allows you to change the allocation of variables to the register number easily. For example, say I have used R1 to do some specific computation. Now I don't want to use R1, say R1 I have used several times in order to perform a specific computation. Now instead of R1 I have to use R2. What is that I have to do? I have to go to my program, say I used it 50 times, I have to change R1 to R2 50 times. Instead of doing this, if I have given an alternative name, say IRN0, now I can just change this. Instead of IRN0, I can make it as IRN1. Now everywhere, my I will become a register R1 now. So that is one important benefit of using an alternate names. And it also allows you to use different register names for the same physical register number. Now in case I want to use multiple alternate names for the same register number, then it is possible. That means I can call the same register number using multiple names. That means say register R0, I need an alternate name I, and for again the same register I need one more alternate name, say J. That is possible. IRN0, JRN0. You can do that. And one more important benefit is it increases giving the names to the registers instead of the register number, increases the clarity and readability of the assembly code which you write. So these are the three main benefits of using the alternate names. Now you understood here the benefits of using the alternate names. Now at the same time, there are several situations or the cases where you have to use the physical number of the registers instead of the alternate names. Now what are those cases, special cases where the register numbers is mandatory and you cannot use the register names using the assembler directive rn? Now the first case is the argument registers. Previous class I explained when you are calling the function, the previous class you understood how to call the function which is written in assembly code from the C programming language. When you are calling the function written inside the assembly code from the C programming language, and when you are passing the arguments, so the first 4 arguments gets copied to the register R0, R1, R2 and R3. Now here I cannot go for changing the names of those registers. I cannot use the alternative names. I got to use the register R0 to R3. The first 4 arguments to the function are placed in the register R0 to R3. And if I am passing more than 4 arguments, any further arguments, they get placed onto the stack, and the return value is always inside the register R0. Now when I am returning, now I cannot use an alternate name. It must be R0 itself. And when I am passing the arguments, to the function, so the first 4 arguments get copied to the register R0, R1, R2 and R3. Now this. And the second important case where the physical number of the register is essential is in load and store multiple instruction. Now when load multiple instruction is this and store multiple instruction is this, so they operate on a list of registers in ascending order, order of the register number. Say for example, I have register R0 and R1 appearing in the register list for LDM and STM. Now that the processor will always load or store R0 using the lower address. So that means the register R0, say for example it is load instruction, the register R0 will be loaded with the lower address, the data which is present at the lower address, and R1 will be loaded with the value which is present at address higher to at the higher address. And similarly, if it is a store instruction, R0 will be loaded with the value which is present at the lower address, and R1 will be loaded with the value which is present at the higher address. That is what does the ascending register number. That means this always gets the value which is there at the lower address, and this always get the address which is at the higher address. Now, and another important case where the physical numbers of the register are important is load and store double word. You can also load two words at a time, or you can also store two words into the memory. Now that time you specify the register, one single register, destination register, it automatically takes the very next register. Say if I'm giving this as R0, it will take the next sequential number, that is R1. And if I give this as R3, it will take the next sequential number R4. And again here also the register number is essential, the physical number of the register is essential. So these are the three cases where the register number is essential instead of the register names. Now here these are the benefits of using the register names instead of the register number, and these are several cases where the physical number of the register is important rather than the register names. Okay. Now how to allocate registers when writing assembly. Now we're going to understand this with a simple example. Now suppose if you want to shift an array of n bits. Now I'm taking an array of n bits stored in the memory. I have an example, I'll show you. Now I want to shift these n bits which are stored in the memory upward in memory by k bits. Now I need to shift this n bits which are stored in the memory upward in the memory by k bits, not downward. Downward in the sense the memory address will increase. When I say upward, the memory address will decrease. I got to shift this n bits by k bits upward the memory. Now for simplicity we also assume that n is large and it's a multiple of 256. Now the array of bits what we are saying, now we are assuming n is very large and it is a multiple of 256. Now for simplicity we'll assume now n is a multiple of 256, and the minimum value what you can consider is 256, and the next value which you can consider is 256 into 2. And we also assume that k can vary between 0 to 32. It can take the value 0 to 31, sorry, not 32, because less than we have 0 to 31. That means how many bits you can shift upward the memory, 0 bit to 31 bit. So that the input and output pointers are word aligned. So we are saying they are word aligned. You know, word is a 4 byte. So the input pointer and the output pointer, they are word aligned. That means the memory addresses are in multiples of 4s. That is 2 raised to the power k is nothing but multiples of 4. So block a copy from 1 bit or byte alignment to a different bit or byte alignment. That means when you're shifting, it must be integer power of k. Now you cannot do 1 bit shifting, or a byte alignment is not possible, and such shiftings we block. Now here I have a simple C program in order to shift the data which is available in the memory upward in the memory by k bits. Now C program it is. So this is the out, which is the new address to be computed, and in is the pointer which is pointing to the data which is already stored in the memory location, and n is the total number of bits, and k is the number of bits to be shifted upward in the memory. And inside this function we are assuming carry initialized to 0, and x is the variable which is taken. Now what I'm doing now, x is equal to star in plus plus. I'm just copying the memory word pointed by n to the variable x, and then post incrementing the n. Now after copying the first memory word to the variable x, in is incremented and it is just pointing to the second memory word. Next, what we are doing here is, now x I'm taking this because I got to shift this upward the memory, and left shifting it by k times and adding with that with the initial carry. Now out plus plus. Now what this gives me is the memory address, that the new address which is computed where this memory word should be shifted to upwards the memory. And then carry is equal to carry right shifted by 32 minus k, because you can shift from 0 to 31 bits, and this k can vary from 0 to 31 bits, and you are finding the new carry, and this process is going to repeat until 32 n is equal to n minus 32. Why 32? Because each word is a 32 bit. N is equal to n minus 32, and while n, if n is not 0, you keep repeating this process, and finally return the carry, and this carry will tell you the new address where the current data value gets shifted. Now I have the example for this. Yeah, so this I have taken an example in order to explain this program. The memory before execution, this is what I'm assuming. See, this is the memory address. It's starting from 0, and this is the data inside the memory. You can observe here, this is 0th byte, so this is the first byte, second byte, third byte, and fourth byte. I have, this is my data. Just understand the one which I've written inside the dotted line is my data, Now I got to shift this data upward in the memory. So this is the downward in the memory, and this is upward in the memory. Now I want this data to be shifted here, and what is the address